So what we'll do today is finish up those reactions to begin with, and then we'll go from there. So we got one more to do, and it's that one. So we're working our way through the reactions there. Of course, they're in the notes. I'm on page 762. All right, now what we have there is a distributed load. And the way you handle a distributed load is you break it up into pieces that you can handle. See, we have equations for the centroid of a rectangle, which would be in the middle. So there's the centroid. This would be half of the base, and then the total base would be the distance across. We also have the formula for a triangle. And the centroid there is a third of the base. What we don't have is the centroid for a trapezoid. So what you got to do on this is you got to break it up into two figures and stack them one atop the other. And so what you want to do then would be to find the area of each figure and then put that as a load at the centroid for each figure. So what we would end up, if we did this, and we are going to do it, is two loads at two different distances. Probably going to take moments about A, so you'd want to reference those loads to A. So you want to get the triangular load there, and then the load for the rectangle would be further over. So your two loads are as shown here. All right. So let's find the load for the rectangle and the triangle. So how high is the rectangle? 3,000 newtons per meter. How high is the triangle? Yeah, you got to be careful on that, and yeah, that's what you want. It's 4,200, okay? So what the height of the triangle is the total height of the trapezoid minus the height of the rectangle. So just be sure that you remember to do that, that you subtract off the height of the rectangle. So once you get both of those loads, which would be areas, the heights are the load per unit length, and the base is the distance on the bottom. When you multiply those together, combine them together, you'll get the unit will be newtons, which is what you want. So you're going to get two loads, basically one, and you want to find the distances where they're located as well. So we'll get this load, and we'll get that load right there. And then we want to know their distances as well. So y'all getting to those all right? This is the area of the rectangle, the area of the triangle, and we want to know how far they are from A. This is, this kind of the deal, in engineering. You take complicated stuff, you break it into pieces, you just kind of go through piece by piece. You want to kind of simplify things so you can deal with them. So we're going to take those areas and you get the loads associated with them, get them at a given location. Once you have those, my inclination on this would be to take moments about A, would be the thing to do. Okay. So what for that, this one over here, I think 6,300 is the number on that one. And the other one's 9,000. Does that sound about right for those? We doing all right with that? And then what are the distances there for the triangle? What's the distance? About a meter there. 1.5. So what we're doing for the rectangle, we got a height of 3. That's newtons per meter. We've got 3 meter distance. So that gets us the 9,000 newtons. And then we're going 1.5 meters from A. Okay, and the 1.5 comes from taking the total of 3 and dividing it by 2, because you're going 1/2 of 3. The other one's a triangle, so that's 1/2 4,200 newtons per meter times 3, and that's 6,300, and that's at 1 meter from A, and that's equal to 3 over 3, because you're taking 1/3 of 3. Okay, you okay with that? Okay, then you take a moment about A, and now you've got forces and distances, so you can do that. Okay, so just do a moment about A to run the reactions there. So sum of moments about A is 0, and then just get those two forces in there with their moment arms, and then you've got the reaction there at C. So that's how you would approach that, I think. I think RC ought to be about 3,300, I think, when you work it out. The negative means clock on a moment. So that, yeah, the sign conventions for force and moment are different. You know, they're not directly related. Just the fact those are downward forces does not always mean they're negative moments. It doesn't always work out that way. So what I do, I put the numbers in the parentheses. Then after I've got the magnitudes in there, then I look at it. I go, okay, that would come around that way, and that would come around that way. They're both clockwise, so they're minus. Whereas this one will come, there's a reaction force there coming up, RC, and I got RA. So RC would cause a counterclockwise moment. That's how I would look at that. Doing all right with that? Okay. So when you solve for RC, then what you get is 3,300 newtons. So we're doing all right with that? Okay, good to go. All right. And then to get RA, I just go sum of Fy, set that equal to 0. The load is on the left side of the beam, so I would expect RA to be quite a bit higher than RC, and I think that proves out. So I just go sum of Fy, set that equal to 0, solve for RA. What you have then are all the forces acting on the beam, because you got the reactions and you have the applied forces. So we're doing all right with that. So then we go sum of Fy, set that equal to 0. RA up, 6,300 for the triangle down, 9,000 for the rectangle down, and the reaction at C is 3,300. So RA is 12,000. What I got? We're good. Okay. So that's just a bit of a review on reactions. So we went through the basics of it. We went through distributed loads. We had a couple on one, then we did a couple of these others. They're a little bit more complex and more things going on. So that's what we got. We did a cantilever reaction too. We just want to be able to handle those because the statics is pretty fundamental with some of the other things we're going to do. So we got to find those reactions first. All right. Now let's get shear and moment would be next if we're good with that. And this stuff, it's a little bit involved. There's two ways to do it. You can do it with equations and diagrams. We'll start with the equations, then we'll come back and get the diagrams. So we'll do that, okay? So we'll start with equations. So here's how this goes. Our goal here is to know what's going on inside the beam now. Okay, and that's what we do in strengths. We go inside of things. So we are going to start at one side of a beam and work our way over. Generally speaking, you start at the left and work to the right. You have to know the reactions before you do this. So the first step is to find the reactions, at least reaction on the left side of the beam. Then you make a cut through the beam at the spot where you want to find the internal shear and moment. Draw up a free body diagram and then write equilibrium equations. Because what's happening here is we work our way across the beam is each section of the beam is in equilibrium and is being held in equilibrium by the internal shear and the internal moment. Okay? So we want to solve for those. Now there is a sign convention here. I mentioned that last time briefly. As you work your way left to right, the moment curls the beam up. So, you know, that makes the beam smile, so that's positive. Curling down makes it frown, so that's negative. Now, the shear is kind of a funny one, though. Shear, as you work your way left to right, which we normally do, is positive down, okay? So we have to remember that. Okay? And this is on page 750, is where I'm at. This is stuff. We're going to jump right on ahead here. So what we're going to run statics equations and solve for those internal force and the internal moment. That's what we're going to do. All right. So let's go ahead to 770. And what we have there is a cantilever beam with a triangular load. And we already found the reactions for it. We did that on page 762. So I went ahead and I just wrote down that information there. I think I did anyway. Maybe I didn't, but did I put that on there? I don't know if I did. So anyway, we have that lined out there. Actually, I did. Yeah, I did it on page 770 where we're at. Okay. So we've already done that, so I just reiterated it. So what we have then is a reactive force of 4,050 up at A and a reactive moment of 2,250 counterclockwise. Okay. All right, so we start with that. Now what we're going to do then is we're going to look at that beam. We want to find the internal shear and moment that's happening inside the beam. So we do it for different sections. From A to B, I've got one loading condition, which for this case is kind of simple. It isn't any load at all. So I'm going to start from A to B, all right? That's how I'll start. So that'll be the first section I work with right there. But once I get to B, I have a load introduced. So that changes what I have to analyze. So from B to C, I'm going to run a second set of equations. Okay, I can't run one set of equations for the whole beam because the load's changing. So what I need to do is write a free body diagram that will hold for a section of the beam. And the first one I can do is from A to B. So I've got the beam written there for you. And what I want to do first is get a free body diagram of that thing going. Okay, and this one's going to be quite simple because there's no loading there. Now on the left, I show the reaction, so I got 4050 newtons, and then I've got that couple, which is, what is that, 2250 or something? Yeah, 2250. Okay. Now, as I work my way from A to B, you'll notice there's no load in there. So I don't show anything on the beam except when I get to the end, because what I've done there at any place, I'm kind of, as I'm working my way across, here's my free body diagram, I'm cutting through the beam. And when I do that, the internal forces then become something that I have to analyze. So the shear there down will be the shear anywhere between A and B, and the moment up will be the moment anywhere between A and B. So there's my free body diagram, like so. Okay. So that'll hold anywhere between A and B. So anywhere between 0 and 2 meters, that'll hold. Okay, that'll work. All right, now the next bit on this is just to solve for the unknowns. The unknowns are the internal shear and moment at the cut. So I just do equations there to do it, just to write up equilibrium equations. So I'll go sum of Fy is 0, 4,050 newtons up, minus VAB down. Okay, that'll be the sum of Fy equation. So when I solve for VAB, it's pretty simple. It's just a number, 4,050 newtons. So the shear anywhere from A to B is 4,050 newtons. So if I'm going to design that beam, that's the shear I'm going to design it for. Okay. Now, the cut is right here. That's where I've cut the beam. I call the distance from the left-hand side x. That's the distance. So if I want to start to write up an equilibrium equation there for the moments, what I've got is I've got a couple there of 20,250. That's Newton meters. It's counterclockwise, so it's positive. Okay. Then I've got the 4,050 newtons times the moment arm of x. It's going to come clockwise, so that's going to be a negative. So there's an example of when the force sign convention and the moment sign conventions don't agree. The force is up, which is positive, but it creates a clockwise moment, which is negative. So that's a minus 450. Okay. And then I've also got the couple there. Okay. Now the couple is counterclockwise, so that'll be plus MAB. Like so. So now I just need to solve for the internal force. Now I don't include the VAB because the VAB has a 0 moment arm. So I don't put it in the moment equation because it zeroes out. So it doesn't cause any moment about the cut. Okay. So there you go. So now I just need to solve for MAB. What I do. So I've got 0 is 20,250 minus 4,050x plus MAB. I bring the MAB to the other side of the equation. When I do that, it becomes negative. Then I'll multiply through by -1, and I'll get MAB is 4,050x minus 20,250. All right, so there now what I've got are equations that will tell me what the shear and moment are anywhere between A and B. Now when I first wrote that equation out, I put units in it, newtons and meters. When I actually do those equations, normally I don't. You know, the units just start to clutter things up. When I start throwing in newtons and meters and x's and all this, it gets a little messy, so I don't put units in it. I just make sure my units are consistent when I start, and then I'm good. Okay. So now, if I plug anything between 0 and 2 into those equations, I can find out what the shear and moment are at any given location. Okay. And that's internal inside the beam. The other thing I'll notice here is if you take a derivative of the moment, you get back to the shear. So that's a good check on your work, if you ever want to do that. So we're doing all right. Good to go. All right, now that's a simple one to start because it had no load on it, okay? Now let's have a look at the next one, which is a little bit more complicated. So we're going to go from B to C now. Okay? So now we're going to make a cut somewhere between B and C, and we're going to find the internal shear and moment anywhere between B and C. So when I make that cut, I get the diagram shown on the right. So I want to get everything filled in here. So I'll start on the left. And what I've got there is 4,050 newtons. And then I've got 20,250 Newton meters. That's over there on the left. Now I also pay a bit of attention to my dimensions. The distance from the left-hand side is x. This is 2 meters here. So this little gap here is whatever x is. And the x will vary from 2 to 6.5 as I work my way from B to C. So in that gap, I got x minus 2. Okay. Now, I want to figure out that area of that triangular loading diagram as it increases. So to do that, I'm going to go through a series of steps here. The slope of that line is it rises to 1,800 over a run of 4.5. So what that means is the slope is 400. And I'm just taking the height that it rises to, which is 1,800 newtons per meter, and that happens over a 4.5 meter run. Okay. So that's the slope. Well, if the slope is 400, the height of that triangle as I work my way across will be the slope times the distance. So that'll be 400x minus 800. Okay, we doing all right with that? Because I'm taking 400 times x minus 2 times 400. Okay. Just what's the word for that? Distributing that through or something? I don't know. There's a word for that. Okay. So that gets me the height of that triangle. So what's going on here is I've got a triangle. I know the slope of this is 400. I know the base is x. So the height is 400x. And actually this base here is x minus 2, isn't it? So this is 400x minus 2. So I just found the height, which is 400 times x minus 2. That's 400x minus 800. So the area then will be the area of a triangle, be 1/2 times the base, which is x minus 2, times the height, which is 400x minus 800. So there's the area of the triangle, the base times the height. Okay. Now I might want to find the area in a little bit fuller sense there. So that will be when I run at 200x squared minus 800x plus 1200. So let's I'm going to take this triangle sketch out, okay? So I got a little bit of room to work there. And I'll go ahead and work through that area. Okay, So what I'd probably do to get this area is go x minus 2. Okay, and I'm going to factor that 1/2 through what's left. So that's 200x minus 400. I'm running that 1/2 through is what I'm doing. I want to kind of get rid of it and simplify things a bit. Okay, then I do the FOIL method, they used to call that. So that'd be what? 200x squared minus 400x. So I'm just multiplying the x through. And then I'll multiply the -2 through. So I'll get negative 400x. And then minus 2 times negative 400, which ought to be plus 800. So I'm getting 200x squared minus 800x plus 800. Is that looking okay? I think it is. All right. Yeah, I think it is. So there we go. All right, so that's the area. Now you can see all those steps down below as I work through the algebra. I'm being very slow and careful on the algebra because I don't want to bust something. I don't want to drop a negative or do any of those things that we do when we start doing too many steps at once. Because, you know, I know beforehand the stuff gets a little bit complicated. All right. All right, so now what I've got is I've got all this stuff pretty much good to go here. So that distance there is x. I've got this area here is 200x squared minus 800x plus 800. That's the area. How about that distance? What's this distance that I've dimensioned right there? How far would it be from the cut, which is the right angle of the triangle, to the centroid of the triangle? That's where I'll apply the load. Yeah, it's 1/3 of the base, and the base is x minus 2. So that'll be x minus 2 over 3. That's a distance. Darn that thing. There we go. That's a distance. So that's x minus 2 over 3. Okay. So now I got that thing all set up and ready to go. So now I just go sum of Fy and I set it equal to 0 is what I do. All right, and so I just start at the left and work my way across. So what do I got? I've got 4,050, that's up, that's that one. And then I got minus that area. So that'll be minus 200x squared minus 800x plus 800. Okay. Let me get this out of here. And then I've got minus the shear from B to C. Okay. Now I got a negative VBC there, so what I can do, I can take that to this side of the equation and it'll become positive. And then I've got what's left over. So what's left over is negative 200x squared minus a negative 800x, so that's plus 800x, minus 800 plus 4050, which comes out to be 3250. So there's my shear expression right there. Doing all right with that? VBC is right here. It's right where the cut is. Good. Okay. All right. So now, see, I've got everything lined out. I got all the numbers I need to plug into the equation up above. So it's just a matter of plugging them in, then working real carefully through the algebra. That's kind of the strategy here. I don't try and do too many steps at once. I get everything lined out first, forces and dimensions, and then once I've got that, then I can go ahead and and set up my formula. Okay, what do we got for this other one? I've got 4050, and I won't bother with the units here. and I'm going to multiply that by the moment arm, which is x. And then I'm going to look at that, and that will come around clockwise, so that's going to get a negative sign. So that'll be negative 4050x. Then I've got the 2250. Okay. Then I've got that downward load. Okay, now I look at that thing, and that thing's going to come around that way. That's counterclockwise, so that's going to get a plus. And the load is 200x squared minus 800x plus 800. Then I'll put a parent on the end of that, and I'll multiply it by the distance, which is 1/3 of x minus 2. And then I'll add in the couple at the end there. Okay. So I've got everything lined out. I've got the 4050 moment arm of x. Because what I'm doing here, I'm taking moments about the cut is what I'm doing. And the cut is right there. That's the cut. That's where I cut the beam. Okay. And kind of taking a moment about that. So 4050 times x plus 2250. The 2250 is the couple over here. Then plus the area of the triangle times the moment arm. So there's the area of the triangle, there's the moment arm. Then I have this couple right here that I'm solving for, MBC. All right. Pretty exciting stuff there. And then I'm going to take that and I'm going to take it to the other side of the equation. It'll become a negative, and then I'll start to collect terms. I just put everything I've got here. Then what I'm going to do, I don't like that x minus 2 over 3 to multiply by, so I'm going to take the 1/3 and put it out front and leave the x minus 2 behind. Then I'll multiply the x through, so that'll be 200x cubed minus 800x squared plus 800x. Then I'll multiply the negative 2 through, and that'll be negative 400x squared minus plus 1600x minus 1600. Then I'll combine all that stuff, and I'll get this. I've still got that 1/3 out front. So I just did, it's not quite a FOIL now, because I got a cubic multiplied by a binomial. I don't know what you would call that, but I'm multiplying the x through each term, and then I'm multiplying the negative 2 by each term, and I'm adding up the results and collecting terms. Then I divide by 3, and I get to this expression. Then I collect all the terms and get them in the proper order. I've got negative MBC over here because I took the positive MBC and I brought it to the side of the equation. So then I multiply through by -1, and I got that. Okay. Now if I take a derivative, which might be a good idea on a complicated one like that, I'll get back to that Shear equation. So that's how I get that. All right. Got any questions on that so far? Okay, we got another one to do as well, though. All right. Okay. All right, the other one, kind of look at that. Went ahead and did the reactions on that. Got the reactions. We did that earlier. So we got 12,000 on the left, 3,300 on the right. All right, now what I want to do is let's see, I have to make 2 cuts on this one between A and B, and the next between B and C. So I'll come up with the area of the triangle and the area of the rectangle, and then find their distances there from the cut, where I'm going to take the moments about. All right. So what I have to do here is I've got to find some information about the height of that figure there on the right. Okay. So to do that, I'm going to need a slope. So what's happening there is I've got a height of 7,200 right there. That's the height. Now the slope of this thing, let's have a look, because what it's doing, the slope, I'm just writing here because I have the room, I'm dropping 4,200. Okay. Now that 4,200 comes from taking the difference between 7,200 and 3,000, and that gets me 4,200. Now I'm going down though, so I'll put a negative in front of that, and then that's happening over a run of 3. So the slope there is negative 1,400. That's the rate at which the top of that trapezoid is falling. So if that's the case, this value right here, what that's going to be is I start at 7,200 and then I drop by 1,400x, I think is what's going on there. Okay. And if that's the case, then I can get the height of the triangle and the height of the rectangle, because that's 4,200, or excuse me, 7,200. This is 7,200 minus 1,400x. So what that leaves on the top is the difference, and that's just 1,400x. Okay. So the height of the rectangle is 7,200 minus 1,400x. The height of the triangle that sits on it is 1,400x. And that has to do with the slope of this line. That's kind of the key thing, is negative 1,400. That's where this all comes from. And then we've got our lower dimension here is x. Okay. So wherever we started, which we started at 7,200, we take away the slope times the distance to get the height on the right. So we doing all right with that? Okay. We got x over 2 here. It's half, that's the distance to the centroid of the rectangle. Now I want the centroid of the triangle. Now I'm coming from the vertex of the triangle, so that'll be 2/3 of x as I come over. Okay. All right. Now the area of the rectangle is going to be 7,200 minus 1,400x. That's the height of the rectangle times the base. So that's going to be 7,200x minus 1,400x squared. And the area of the triangle will be 1/2 because it's a triangle, and the height is 1,400x, and the base is x. So that's looking like 700x squared for the height of the triangle, or the area of the triangle. Okay. Yeah, this stuff's fairly complex. You got to do a bit of geometry, right? So the whole thing, step by step by step. Just, you know, don't rush. Don't combine steps. Get pictures with dimensions, and everything just generated systematically every little step of the way. That's how you want to do this. All right. Now I know the reaction on the left is 12,000, isn't it? Kind of my recollection there. I think it is. So if I go sum of Fy equals 0, that's going to be 12,000 up. I got to take the two areas down, so it'll be minus 700x squared. That's the area of the triangle. And then minus the 7200 minus the 1400x for the area of the rectangle. And then I'm going to have minus the shear value, minus VAB. So there's my sum of Fy equation.
The part in the parentheses, what part was that?
That is the area of the rectangle, which has a height of 72. Oh yeah, I forgot the x and the x squared in there, didn't I? So I need an x in there, and I need an x squared for the 1400 bit. So that'll be x and then minus, and that should be an x squared, like so. All right, bring the VAB to the other side and collect terms, and I get this expression for the shear. Now the sum of moments about the cut. Again, just one step at a time there. I've got the 12,000 on the left for the reaction, moment arm of x, clockwise, so it's negative. Then I've got the area of the triangle. And what I've got there is, its area is 700x squared. That's the area of the triangle. And the moment arm for that is 2/3 x. Okay. So what I've got going on there is I've got the area and the moment arm. Now that's going to come around counterclockwise, so I've got a plus there. And then I will also have the area of the rectangle, 7200 minus 1400x squared. That's the area of the rectangle, and its moment arm is x over 2, and that will also be positive. Okay, so that one and that. What's that now? Behind the 7200? Yeah, okay, thanks. Okay. There we go. And then I have my plus MAB. So that's the shear and moment. Inside of that, you can again take the derivative of the moment to check it. You should get the shear. I don't know if I still have the typo in your packet or not. I don't? Is plus in there? Is it now? Okay, so I fixed that. So this should be plus here. That should be plus. Oh shucks, what's going on there? Why do I have a negative in there? Something's not looking right with that. I don't know quite what. Because it's carrying all the way through, isn't it? I don't like that. What's going on? All right. All right, well, we're about out of time, so I have to look at that a little bit. What sign do y'all have right there in your packet? Yeah, it should be. Does that number still work out to be 233 x cubed? Yeah. As you work your way down through the algebra? Oh, because there's a minus here, but we got a minus there. Okay, I have to kind of look through that. I'll look at the signs. We'll take care of this on Friday. So we got that test coming up on tomorrow. Okay, so we good on that? Okay.